Hello, welcome to your video about kinematics. Kinematics is a branch of physics dealing with motion, which includes motion, velocity, and acceleration. This is kind of a big idea in the world of science and physics, and it's a great connection between calculus and physics as well. So be ready to take some notes. If you haven't yet printed the one-page notes page that I sent to you, make sure to go print that, and then you can take notes right on there. All right, so first of all, you're given a graph there. The graph, it says, is uh, the motion of you throwing a ball. So here's time, here's height. So obviously when you throw a ball up, it begins at a height of 0, it goes up, reaches some maximum point, and then goes down, and eventually lands. In this case, everything's diagrammed there. This is the equation of that function. It's a quadratic, you can see. And this is called a position function. Basically, it means that every point on here represents the position of the object at a certain moment of time. So it's S is represents position and T based on time. So based on time, here are all the different positions of the object as it is flying. All right, so here are the questions you will answer. Number one, at what time is the ball at its highest? So these questions should be pretty simple, but they'll lead into the main ideas of the calculus and everything that we're going to use to work on this problem. All right, hopefully you got an answer of t equals 3, and you can see it right here. The ball's at its highest right there, and that is at a time of 3. So right in the middle of its motion here. All right, how high is the highest point? So how high does a ball go? All right, hopefully you got 9. If you follow the ball here, it's going up, and it gets to this highest point, which is at 9. And we don't know if this is feet or meters or what, but anyway, 9. 9 right there. Number 3, when does the ball have the highest velocity? This one might be a little trickier, so think about it. Think about throwing a ball, and when would that speed, velocity means the speed, right? When would the speed of the ball be its highest? All right, the answers for this one are at time equals 0 and time equals 6. Let's take a look at that. So time equals 0 is right here. Basically, right at the beginning, it has its highest velocity. That might seem strange because you're right at the beginning, you're holding the ball, right? But also the beginning is the moment that you throw the ball, the very moment that you just release the ball. And if you think about that, that makes sense. The ball, the moment you're releasing it from your hand, which is right here, it's going its fastest because you have all this force from your hand, and that ball right now is going its fastest. And then the ball goes, let's see, the ball goes up, 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 up. And what happens as it's going up? What happens to the speed? All right. Um, that's going to be the next question, but let's look at this. When is the ball the fastest? So the moment it leaves your hand, it's at its fastest, and also the moment it hits the ground or comes down again, because here it's going from the top and it's just falling, falling, falling faster, 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 and the moment it hits the ground, it's also going at its fastest. So those two moments in time are when it's going its fastest, highest speed. So number 4, what is happening to velocity as the ball goes up? So as the ball goes up to its highest point, what is happening to the speed, the velocity? Hopefully you put it's decreasing. Yes, so when the ball leaves your hand, it's at its highest speed, and then it's going up. And as it's flying up, the ball is going against the force of gravity, right? So gravity is trying to pull the ball back down. So actually, as the ball is going up, the speed becomes less and less and less. So the speed decreases because gravity is trying to pull it down. And eventually, gravity wins. The ball is pulled down from there onwards. So the speed is getting less, less, less. All right, when does the ball have no velocity? The answer for that is at time equals 3. So right in the middle there, when the ball is at its highest point, it has no velocity. There's no speed. Again, fastest speed here when it leaves your hand, then it's flying up, flying up. The velocity is getting less and less and less. Gravity is making it slow down. It gets to its highest point. At that moment in time, the ball is just sitting there and it has no speed, no velocity. And after that, it's going down and the velocity is it's gaining some velocity again. Number 6, what has happened to velocity when the ball is falling from its highest point? So what's happening to velocity here? Hopefully for that one you see it's increasing, all right? So it starts again, super fast velocity, slowing down, gets to its highest point. It's kind of sitting in the air there, no velocity, and then it's falling. And as it's falling, the speed is getting faster and faster and faster and faster. So the velocity is increasing on its way down. All right, so those are some basic questions to get us started on the ideas of position functions, velocity, acceleration, and I hope those make sense. Let's go on. So now question 7 says, considering 1 to 6 above, do you see a connection between velocity and some aspect of the graph? All right, so think about the graph. All right, if you're thinking about the journey of the ball, the velocity is the slope, and this is the big idea we've been talking about in calculus. The slope of a graph is its rate of change, and in this case, the velocity is represented by the slope. So at each moment in time, if I go back, at each moment in time, if you drew a tangent line and found the derivative, that would be the slope, and that slope there represents the velocity. So for example, here the slope is the highest, so it has its highest velocity. And as you go, the slope is less. So imagine tangent line is less. And here the slope is even less, so less velocity. And finally at the top, the tangent line goes across like that. So there's no slope, and then we said there's no velocity, right? And then there's a little bit of downward slope, and then more slope, and then even more slope downward, so faster negative velocity. All right, so I hope you see that relationship. That's the key idea for today, really. We'll come back to that and make an equation in a moment. First, number 8. So here's our motion again. It says draw a motion diagram. Motion diagram is a kind of a diagram that's often done in physics to show the motion of an object. Basically, it shows how the object moves away from its starting position and then comes back to it. So we're going to draw a very simplified motion diagram, but these can get more complicated. So first of all, in the beginning, the ball starts right here in the beginning, time equals 0. And then the ball moves away from the starting spot. And by starting spot, I mean it started at 0, the height was 0. So the ball moves away, that means the height is increasing. It's going further and further away from its starting place. And then at some moment, something happens, and that moment is time equals 3. So at time equals 3, right here, the ball actually turns around and starts coming closer to its starting place, which was the ground. So it moves away from the ground, and then at 3, towards the ground. So on the motion diagram, you would wrap that around and then go like that. Now it's going back. So this is moving away from the ground, and now it's coming towards the ground, and that change happens at t equals 3. And then it says draw the motion diagram for t equals 0 to 5. So only from 0 to 5. So if you follow this, from 0 it goes up, reaches there, and then it goes down, and at 5 it's here. So at 5 it hasn't reached the ground yet. Actually here, if you keep following, at 6 it reaches the ground, but at 5 it's still here. So that's why this motion diagram stops here, because you're moving away from the ground, come around, now you're moving towards the ground, but at t equals 5, you're not back at the ground yet. If you had to draw this motion diagram all the way to t equals 6, then you'd continue this all the way here, and you'd end up back where you started. So it would be all the way like that, and time equals 6 would be here. That leads into the idea of displacement and total distance. This should not say change in displacement, it just should say displacement. Okay, so you cross out change in. All right, displacement. So displacement is the physics word for the net change, like how much has something moved. And again, when the ball goes up here and then down again, it's moved away from you, from the starting position, and then moved back towards you. If you look at the beginning and the end, what is the net result? It doesn't really matter what happened. In the end, the ball is right back where it started. It started at 0 meters, it is back on the ground again at 0 meters. So displacement just says what happened in the end. What is the net result? The net result is it didn't move. It's kind of funny to think about it that way, but it went up 9, then down 9. The end result is like it hasn't moved at all because it's back where it started. So the displacement is 0. So that's what displacement is. And then this contrasts to total distance. Total distance now is different. It's saying how much has it moved altogether. In that case, up 9, down 9, total distance is 18. So make sure you understand the difference between displacement and total distance. All right, now let's get the functions. Here's your position function. That's the original parabola. Velocity, we talked about. Velocity is your derivative, right? It's the tangent line at every point. So if you find the derivative of s, if you find the derivative of that function, you have the velocity function because it gives you the slope of the tangent at every point. So that's velocity. So in our situation, here's the original function. Take the derivative of that. So velocity is the derivative of the position function, and if you take the derivative of that, you get this. All right, so here's our velocity, negative 2t plus 6. Now let's fill this table. In the table, we can fill in the velocity at every moment. So let's go to 0 first. Put 0 into here, because this is our velocity function. Put 0 in there, negative 2 times 0, 6. So 6 is our velocity. All right, now let's put in 1. So put 1 in here, and you get 4. Now put in 2 at time equals 2. Put 2 in here, and you get 2. Now put in 3. You finish the rest of the table, and let's see what answers you get. At 3, it's interesting, velocity is 0, and then negative 2, negative 4, negative 6. So let's talk about that for a moment. We said in the beginning, when the ball leaves your hand at time equals 0, it has its highest velocity. And there's 6, velocity is 6. And then when it arrives on the ground again at time equals 6, it also has its highest velocity. Those are the two highest velocities. It's a positive velocity because it's moving away from you, and here it's the same velocity, 6, but it's negative because it's coming towards you. So see the two highest velocities at the beginning and at the end when it's just about to hit the ground. And then here the velocity is getting less and less, right? We saw that on the graph. It's going up, gravity is working against it, the velocity decreases, and then it gets to its middle point, the point where it's just kind of sitting in space at the highest point before it starts dropping again. At that moment, remember the velocity was 0. It's the top of the parabola, and the tangent line has a slope of 0. There's no velocity. It's just sitting in space at that one spot. And then it starts falling, and it falls quicker and quicker and quicker, and the velocity is the fastest. So that should make sense. Hope you understand these key ideas here. Now let's look at the acceleration function. So acceleration is actually the slope of the velocity graph. So acceleration basically tells us how quickly is velocity changing. So velocity is telling us how's the position function changing. Now acceleration is telling us how the velocity function is changing. So the velocity function change will be the derivative of the acceleration will be the derivative of the velocity function. Or another way to look at that is the second derivative of the position function, because if you take the derivative of position, it gets you this, then take the derivative again, it gives you this. So acceleration, here's our velocity function, which we just found. Now we're going to take the derivative of that to find acceleration. Take the derivative, and this one becomes a very interesting derivative, it just becomes negative 2. So what this is telling us is the acceleration of our flying object is negative 2. So the acceleration at any moment in time is always negative 2. Now let's think about that. The connection here is very interesting and important. So let's look at our table again. Here's our table. And the velocity as we go, right, starts off fast, slowing down, no velocity at its highest point, and then increasing but negative velocity. Now look at what the difference between each of these values is. Minus 2, minus 2, minus 2, minus 2, minus 2, minus 2. So the acceleration tells us how the velocity is changing. That's what this derivative means. And the velocity is changing by minus 2 for every unit of t. All right, so the velocity is going down by 2 every time. So all these connections are super important. Hope you're understanding it. Ponder that, talk with your group if you need to, and once you're ready, you're going to begin on the textbook assignment related to these problems. Some of them will seem easy, hopefully. Use the examples in the textbook, they will help you with the problems for sure, and let's see how you do. Oh, one more thing, that's right. You're going to add the velocity graph and acceleration graph to your original. So here's the position graph showing the flight of the ball. Now, velocity function is this. This is a line, all right, with a y-intercept of 6 and a slope of negative 2. So, and there's the acceleration. So here is the velocity function, right? Here's the y-intercept of 6 right here. And here's the slope. It goes down 2 over 1, down 2 over 1, down 2 over 1. So here's the motion of the particle, of the ball. Here's the velocity, and we know the velocity starts at 6 right here, the velocity was 6, and then the velocity just keeps going down, right? It's getting less and less and less. The velocity is 0 right here, so let's follow it. Velocity is going down, going down. Oh, right here, at time equals 3, velocity is 0, and then the velocity is negative, but increasing negative, and that's what's happening here, right? Negative velocity, negative, until right here when it hits the ground, remember it had a velocity of negative 6, so down here, if that kept going, we'd go to negative 6 right here. So that's the velocity. And then acceleration was negative 2. This is just the line y equals negative 2. So the acceleration is right here. And again, the acceleration is constant. It's always decreasing the velocity by negative 2. So there's the acceleration. All right, we'll do a lot more of that stuff after the break, but for today, again, focus on the assignment. Here's the assignment you should be working on. The assumption is that you're done with all these problems when you return from the break. We'll kind of jump into a brand new topic, so it's up to you to really figure these out and understand it. It's not a huge part of the IB curriculum, but you may see a question on acceleration velocity on the exam, so make sure you give these a try and figure out what you're doing. All the best, and see you guys soon. You can do it.